Something really weird is happening to Earth, and almost nobody is talking about it. Your days feel normal, but the data says our planet has started behaving in a way that doesn't fit the rules we thought were solid. In this video, we're going to unpack what the numbers are screaming, why scientists are on edge, and what it means for the way you experience time itself. You're told a day is 24 hours long, 86,400 seconds solid, fixed, done. But that's not actually true. On June 29th, 2022, Earth completed one full rotation about 1.59 milliseconds too fast. That means the planet finished its spin slightly early, so that day was 0.00159 seconds shorter than the official standard your clocks are built around. That number sounds tiny, so let's ground it. At the equator, the surface of Earth is moving at about 465 meters per second, roughly 1,670 kilometers per hour, about 1,040 miles per hour. If you cut 1.6 milliseconds off the spin, the surface should have carried you about 700 meters farther, around 0.7 kilometers, about 0.4 miles. That distance simply didn't happen because the planet stopped the rotation a little early. You didn't feel any of this. Your body can't detect a change this small. There was no strange wind, no dizziness, nothing. But atomic clocks did feel it, in a very strict way. These clocks, based on cesium atoms, define 1 second by counting a fixed number of atomic oscillations. They tick billions of times per second and stay in sync across the planet. When they say the day ended early, it ended early. They are not guessing, they are measuring. So the first weird fact is simple: you really did lose about 1.5 milliseconds of your life that day, and there was no option to opt out. The planet spun, clocks recorded, and the day closed out slightly faster than expected. Now here's the next question. Was that a one-off freak event, or part of a bigger pattern? From the 1960s through the 2010s, Earth usually ran a little slow compared to the perfect atomic day. Its rotation was slightly longer than 86,400 seconds. To keep civil time, the time your phone shows aligned with the actual position of the sun in the sky, timekeepers sometimes had to add leap seconds. That's when a day officially gets an extra second, and you see a minute that goes 59, then 60, then 00. All of those were positive leap seconds, because Earth was lagging behind. Then 2020 arrived and the pattern changed direction. That year contained 28 of the shortest days recorded in the high-precision era. Many of them were more than 1 millisecond shorter than the standard. After decades where the planet tended to be slow, suddenly it was often fast. Think about the logic shift. We built our time rules on the idea that long-term, Earth is gradually slowing down, mainly because the moon's tidal pull is stealing rotational energy, so we expected to add seconds once in a while. Instead, our real data started showing that the planet was, for a while, spinning slightly faster than the atomic baseline. The sign flipped, so you have to ask, is this just random noise around a slow trend, or has something important changed in how Earth moves? If it was only 2020, maybe you'd say it's a short-term fluctuation, but jump ahead to the mid-2020s. In 2025, some days are again showing up about 1.3 to 1.5 milliseconds shorter than 86,400 seconds. Some specific days in July and August line up as some of the shortest days since we started tracking this with the best instruments. Again, you cannot feel a 1.5 millisecond difference. A blink is around 1/10 of a second, 100 milliseconds. The changes we're talking about are almost 100 times smaller than that. For your body and your daily routine, it might as well be nothing. But for your technology, it is absolutely not nothing. GPS is a clean example. GPS satellites orbit at around 20,000 kilometers altitude, roughly 12,500 miles, and they rely on precise timing to tell you where you are. Light travels about 300,000 kilometers in 1 second, about 186,000 miles. In 1 millisecond, light travels about 300 kilometers, roughly 186 miles. The system geometry and correction models reduce the full effect. But if you let Earth's rotation drift by a millisecond and do not adjust your calculations, position errors can easily grow to hundreds of meters or more. It's not just GPS. High-frequency trading systems, telecom networks, power grids use precise timestamps to coordinate events. They assume that the relationship between clock time and Earth's rotation is known and regularly updated. When the planet's spin rate changes in an unusual way, all those systems have to be updated faster and more carefully. If they are not, things go wrong. So now we hit the core problem. Our main time standard for the planet, called UTC, is locked to both atomic clocks and Earth's rotation. It has to stay within 0.9 seconds of a rotation-based timescale. For decades, the fix was simple: add a leap second once in a while when Earth ran slow. But if Earth keeps running fast, we eventually face the opposite problem. If the planet spins ahead far enough, the only way to keep UTC and rotation-based time close would be to remove a second from the clock instead of adding one. That is called a negative leap second. Instead of a minute that goes 59, 60, 00, you would have a minute that goes 58, then jumps directly to 00. 1 second never happens at all. You might ask, who cares? It's just one missing second, right? But a lot of global software has never seen a negative leap second. Many systems assume that days can be 86,400 seconds long or 86,401 seconds long on a leap second day, but never 86,399. A negative leap second would break that assumption. Some code would need to be rewritten. Some devices would need firmware updates. Every system that relies on strict time order would need to be tested in a scenario that has never actually occurred in reality. We already know that even positive leap seconds can cause trouble. In past leap second events, some servers froze or crashed, some databases got duplicate timestamps, and some services briefly failed because they weren't written to handle a 61-second minute. Now, extend that to a situation where we try to delete a second instead. Something nobody has actually implemented in live global infrastructure. So the weird thing that is happening to Earth is not just that days are slightly shorter. The deeper issue is that this small change in rotation speed pushes right against the design limits of how we keep time as a civilization. A few milliseconds shaved off a day sound harmless, but at the scale of the entire planet's systems, they force discussions about whether we should cut a second out of history, or even change how UTC works in the long term. The real tension here is simple. The planet is following physics, not human schedules, and right now, its rotation is not behaving as smoothly as we expected. You are living in a period where Earth's spin is strange enough that experts are seriously considering doing something no one has ever done before with the world clock. So the next natural question is, how fast is Earth actually supposed to spin, according to the basic physics, and why is it allowed to drift at all? Earth's spin is not just a vague about 24 hours thing, it's one of the most precisely measured motions in the solar system, and it still refuses to behave perfectly. You live on a planet where we can write down, in hard numbers, how fast it should be rotating, and then the planet quietly drifts away from that prediction by milliseconds. That gap between should and does is exactly where this whole story starts to get tense. First, the basic numbers of your spinning home. When scientists talk about Earth's rotation, they often use what's called the sidereal day. That's the time it takes Earth to do one full turn relative to distant stars, not relative to the Sun. That sidereal rotation rate works out to about 7.3 times 10 to the minus 5 radians per second. In plain language, that means one full spin in roughly 23 hours, 56 minutes and 4 seconds, slightly less than 24 hours. The 24-hour day the solar day, is a little longer because while Earth is spinning, it's also moving along its orbit around the Sun. By the time you've done one full turn relative to the stars, the Sun is not in exactly the same spot in the sky, so you have to rotate a bit more. That extra bit stretches the sidereal day out to the familiar 24-hour solar day. At the equator, that rotation speed is about 465 meters per second, roughly 1,670 kilometers per hour, about 1,040 miles per hour. You, sitting still in a chair, are being carried around the planet at jetliner speed just because Earth is rotating. And the key point is, That spin rate is not a guess. We measure it with radio telescopes, satellites, and atomic clocks. We know exactly how fast the planet is turning down to tiny fractions of a millisecond. So here's the obvious question. If the rotation is so well defined and so carefully measured, why isn't it perfectly constant? There's a simple big picture answer you've probably heard before: the moon is supposed to be slowing us down. The gravity of the moon raises tides in Earth's oceans and even in the solid rock. Those tides rub against the seafloor and the crust, and that friction eats away at rotational energy. The angular momentum, the spin momentum of Earth, doesn't vanish. It mostly gets transferred into the moon's orbit, pushing the moon slightly farther away over time. Over millions of years, that process adds up. Geological data from ancient tidal rocks and fossil corals, plus historical records of eclipses, all point to the same conclusion. On long timescales, the length of the day increases by about 2 to 2.4 milliseconds per century. That's a couple of thousandths of a second added to the day every 100 years, averaged over long periods. So the long-term story is supposed to be simple. Earth spins, tides act like a brake, the moon slowly drifts away, and days slowly get longer. That's the baseline physics. So if the moon is always applying this brake, why are we suddenly seeing days that are shorter, not longer? This is where the clean long arc meets the messy short-term chaos. Over tens of millions of years, yes, the day grows by a few milliseconds per century. But over years, or decades, the length of day can swing up and down by comparable amounts because of systems that are much more dynamic than lunar tides: the atmosphere, the oceans, and the liquid outer core. The atmosphere alone is a massive shell of air, about 5 times 10 to the 18 kilograms. When winds shift, when jet streams strengthen or weaken, when large-scale pressure patterns move around, that mass redistribution changes how the planet's mass is arranged. The oceans do the same thing, moving huge amounts of water between basins and latitudes. Deep below, the liquid iron outer core flows and interacts with the mantle. All of these things can slightly speed up or slow down the rotation on timescales from days to decades. So the overall trend is longer days over millions of years, but riding on top of that is a noisy pattern of shorter and longer days, sometimes by a millisecond or more. Right now you're living inside a local spike of shorter days, a downward blip on top of that slow upward curve. The moon is still applying the long-term brake, but other processes are temporarily overpowering that effect and making the planet spin a bit faster. That leads to the next key point. If these wiggles are only a millisecond or so, why does physics treat them as a big deal and not just as rounding error? To answer that, you need to think about what actually changes when you shorten a day by 1 millisecond. The rotation period is the time for one full spin. If that time gets shorter, the rotation rate, the angular velocity, goes up. This is just speed in angle terms. How many degrees or radians per second Earth is turning. Even a tiny increase in that rotation rate matters when the thing spinning is incredibly massive. Earth's mass is about 5.97 times 10 to the 24 kilograms. It's not a solid, uniform sphere, but you can still talk about its moment of inertia, basically how hard it is to change its spin. The larger the moment of inertia, the more energy you need to change the rotation rate by a given amount. For Earth, that moment of inertia is huge. When you compute the rotational energy, the energy stored in the spin, it depends on that moment of inertia and on the square of the rotation speed. That square is critical. If you nudge the spin rate a little bit, the change in energy is not just linear. It scales with the spin speed multiplied by itself. So even if the fractional change in the day length is tiny, 1 millisecond out of 86,400 seconds, when you multiply that by Earth's enormous mass and its large moment of inertia, the energy difference is very real. We are talking about amounts of energy in the range of major geophysical processes, things like big shifts in core flow, large-scale changes in atmospheric circulation, or significant mass movements in the oceans and ice sheets. This is why scientists don't shrug off a millisecond change in day length. It's not just a timing glitch. It's a signal that something on a planetary scale has moved or sped up or slowed down. When the day gets shorter by a millisecond and stays that way for a while, that means the planet had to find that rotational energy from somewhere, and some other part of the Earth system had to give it up. And that brings you straight to a more uncomfortable question. If a tiny timing shifts mean massive energy moves under your feet, what happens when those shifts start to conflict with the way we define and distribute time across the entire technological world? Your clocks are loyal to atoms, not to the planet under your feet. That is the core of the mismatch. Earth can speed up or slow down a little, but your second, the thing every system uses, is locked to a microscopic process in a lab, and it does not care what the planet is doing. Modern time is defined using cesium-133. One official S-time second is exactly the time it takes for that atom to vibrate 9,192,631,770 times between two specific energy levels. That's it. No sun, no Earth, no sky, just a fixed count of atomic oscillations. When labs build atomic clocks from that definition, they get a timescale called TAI, International Atomic Time. TAI is brutally consistent. It doesn't know about seasons, it doesn't know about tides, it doesn't know that Earth had a slightly short day in 2020 or 2025. It just counts those cesium ticks, one after another, perfectly even, second after second, for satellites, for deep space missions, for physics experiments. That regularity is goal. But here's the problem you run into. If atoms say this is 1 second, and Earth decides to spin slightly differently, who wins? Astronomers keep a separate timescale that actually follows the planet UT1. UT1 is based on Earth's rotation, basically means solar time at Greenwich, whereas the Earth facing right now written as a time. When Earth speeds up a bit, UT1 runs ahead. When Earth slows down, UT1 lags behind. Because atomic time never changes its pace, UT1 slowly drifts relative to the atomic second. Sometimes the drift is in one direction, sometimes the other, depending on all the small changes in rotation. So you end up with two very accurate clocks, one tied to atoms, one tied to the sky, and they do not stay in sync on their own. So how do you run a world that needs both? The stability of atoms and the reality of Earth turning under the sun. That's where UTC and leap seconds come in. UTC, the time on your phone and computer, is a hybrid. Under the hood it's based on atomic time, but it's adjusted so it never gets more than 0.9 seconds away from UT1, the Earth rotation time. To hold that rule, timekeepers sometimes have to insert leap seconds. Since 1972, we've added 27 leap seconds, and every single one has been positive. All of them were extra seconds added to the end of a day. On those days, the last minute of June or December has 61 seconds instead of 60. Clocks go from 23:59:59 to 23:59:60, then roll over to 000000. Most people never notice, but the time servers absolutely do. Those leap seconds are basically small corrections to keep UTC lined up with the actual position of Earth relative to the Sun. When Earth ran a little slow, we gave it an extra second once in a while so that noon stayed roughly close to when the Sun is overhead. But this whole system quietly assumes one direction, that in the long run Earth is either a bit slow or, at worst, just right. So what happens when the planet starts running slightly fast instead? Because Earth has recently been spinning a bit faster, at millisecond levels, UT1 has at times begun to creep the other way relative to atomic time. That raises a possibility nobody had to deal with before, a negative leap second. Instead of adding a second, you delete one. A negative leap second would mean a day with only 86,399 seconds, a minute that goes 23:59:58 straight to 0000000, skipping 23:59:59 entirely. On paper, it's a clean fix. You keep UTC within 0.9 seconds of UT1. The rule is satisfied. Everything matches the rotation again. In practice, it's a major stress test. Huge amounts of software, databases, and network protocols assume that a day can have 86,400 seconds, and sometimes 86,401, but never fewer. They are written on the idea that you might stretch a minute, but you never delete a second from the timeline. A negative leap second breaks that assumption. We already know positive leap seconds can cause trouble. In past events, some servers locked up at 23:59:60. Some systems wrote duplicate timestamps, some services crashed because they had never seen a time value that didn't fit their internal rules. Now take all that and apply it to a type of leap second nobody has ever actually done live. That's why engineers are nervous. So the obvious question becomes, if leap seconds are this fragile, and Earth's spin is this messy, how long can we keep patching the clock like this? In 2022, international timekeeping organisations decided they had had enough of constant small fixes. They voted to phase out leap seconds by around 2035. The plan is to let UTC slowly drift away from UT1 beyond that strict plus or minus 0.9 second limit, so we don't have to keep inserting these sudden 1 second jumps. Translated into everyday terms, that means humanity is seriously considering loosening the link between clock time and where the sun actually is in the sky. Noon on your watch would still be close to when the sun is highest, but over decades and centuries the alignment would slowly slide. The sun at 12 o'clock might gradually be higher or lower than it is today at the same reading. For most of your life the drift will be tiny, but the principle is huge. To keep global systems stable, we may decide that it's better to let our clock stay loyal to atoms and just accept that the planet's rotation will slowly move out of sync. Time, the thing you assume is tied to the day-night cycle, becomes more of a pure human convention, less of a direct reflection of the sky. And that raises the next, sharper question. If our clocks detach from the sun, because Earth's spin is too unpredictable, what exactly is causing the planet to misbehave in the first place, and how much worse can that get? One of the biggest suspects in this whole shorter day story is literally sitting on top of you all the time, the air. You look up and see a thin blue layer. It feels weightless, but as a system, it's heavy and powerful enough to push on the planet's spin. Earth's atmosphere weighs on the order of 5 times 10 to the 18 kilograms. That's a 5 with 18 zeros after it. When that much mass shifts around, it changes how the weight of the planet is distributed. Physicists call this the moment of inertia, basically how hard it is to spin the planet. If the air moves closer to the rotation axis, Earth can spin a tiny bit faster. If it moves farther out, Earth spins a tiny bit slower. The key rule is conservation of angular momentum. The total spin budget of Earth plus its atmosphere has to stay the same unless something external acts on it. So when high-altitude winds pick up or shift position, the atmosphere can trade a bit of its spin with the solid Earth. Stronger or displaced jet streams can change the length of the day by fractions of a millisecond, and we can see that in the data. You don't notice this in your daily life. When a jet stream over the Pacific speeds up or slides north by a few hundred kilometers, you just see it as the weather. But from the point of view of the whole planet, that is a huge mass of air moving, and the only place for the resulting angular momentum change to go is into the rotation of the solid Earth and oceans. So the obvious question is all this atmospheric chaos just random, or is there a pattern in how it pushes on the length of the day? There actually is a very clear pattern. When scientists stack up length of day measurements over many years, they see a strong annual cycle. Over the course of a year, as seasons change, air shifts between the equator and the poles. In one season, more mass is concentrated closer to the equator. In another season, more mass piles up at higher latitudes. That shifting of mass nudges the moment of inertia up and down, and by conservation of angular momentum, the rotation rate responds. The result is that the length of day oscillates by about 0.5 to 1 millisecond over the year, shorter in some months, longer in others, in a fairly regular pattern. So built into your calendar, buried underneath holidays and school years, there's this invisible seasonal breathing of the planet's spin. Air moves, the effective shape of the planet for rotation purposes changes, and the day length follows, by fractions of a millisecond, over and over again. But if the seasonal cycle is so regular, Why do we still see unexpected spikes like the extreme short days around 2020 and 2025? The answer is that not all atmospheric effects are smooth and predictable. On top of that yearly breathing, you get big dynamical events that hit the system in more abrupt ways. Strong El Niño phases, for example, reorganize convection and wind patterns across the tropical Pacific. Planetary scale waves ripple through the atmosphere. The polar vortex in each hemisphere can strengthen, weaken, or suddenly shift. Each of those events moves mass and momentum around in the atmosphere. A single huge storm system might only change the length of their day by a few microseconds on its own, far below what you can feel. But our instruments pick it up. When similar anomalies persist for weeks to months, they add up. Over a season, you can see clear millisecond-level signals in the length of day record that line up with known changes in wind patterns and pressure systems. So the rotation record is not just a smooth curve with a gentle seasonal wiggle, it's a curve with small but very real bumps and kinks, some of which trace back directly to named events in the climate system. When climate scientists talk about coupling between atmosphere and rotation, this is what they mean. You can literally see the fingerprints of El Niño, polar vortex shifts, and other events in the timing of the day itself that lead straight to the next point. If the atmosphere is doing all this, how does it connect to the specific cluster of unusually short days we see around Northern Hemisphere summer 2025? In 2025, some of the shortest days show up in July and August, right in the middle of Northern Hemisphere summer. That timing is not random. During summer in the north, the temperature contrast between the equator and the pole tends to shrink. When that contrast gets smaller, the classic strong jet streams that depend on that temperature gradient can weaken or shift position. When the jets weaken or reorganize, the distribution of high-altitude winds changes. That means the way angular momentum is stored in the atmosphere also changes. A particular pattern of weaker, restructured jets can hand a tiny bit of that spin back to the solid Earth, letting the planet rotate a touch faster. At the scale of a day, that shows up as length of day values that are 1.3 to 1.5 milliseconds shorter than the nominal 86,400 seconds. So in mid-2025, you are basically watching atmospheric physics translate directly into planet-scale timing changes. No explosions, no disasters, just a quiet shift in wind patterns 1 or 2 tens of kilometers above the surface, and the net effect is that the entire planet's spin rate ticks up by an amount your phone can't feel, but a timing lab can absolutely see. When you put this together, the message is very direct. The air above you is not just a passive blanket, it is an active part of the planetary flywheel. It moves, it trades angular momentum with the solid Earth, and in certain patterns, like those seen around Northern Hemisphere summer 2025, it can push the length of day into record-short territory. And if the atmosphere alone can swing the day by around a millisecond, you have to ask the next question. What happens when you add the mass of the oceans, the melting of ice sheets, and shifting water across the entire globe into the same angular momentum game? Most people think about climate change as a temperature problem, not a timing problem, but the water on your planet is quietly playing with the length of your day. While you're focused on heat waves and sea level, the oceans and ice are also shifting Earth's spin by just enough that atomic clocks can see it. Start with the oceans. They're not just a blue backdrop, they're a massive moving flywheel. Earth's oceans hold around 1.4 times 10 to the 21 kilograms of water. That's a 1 with 21 zeros worth of mass, spread over basins that are thousands of kilometers across, thousands of miles. When currents change, when water piles up on one side of an ocean basin and drains from another, the global mass distribution changes. That mass can move toward or away from the rotation axis. When more water sits closer to the equator, the effective moment of inertia of the planet goes up. It becomes slightly harder to spin, and Earth's rotation slows a bit. When more mass collects closer to the poles, the moment of inertia goes down and the planet can spin a little faster. Models and observations together show that these oceanic shifts can change the length of day by milliseconds over months to years. Not microseconds, milliseconds. That's the same order of magnitude as the weird short day since 2020. A change in how the Pacific and Atlantic slosh water around over a few seasons really can tighten or loosen the planet's spin in a way that shows up in the rotation record. So if the oceans can already nudge the length of your day around, what happens when you start melting the ice that feeds them and move even more mass into those basins? This is where ice sheets come in. Think about Greenland and Antarctica. Right now, a lot of water is locked up there as ice, stacked at high latitudes, relatively close to the rotation axis compared to the equator. As the climate warms and those ice sheets melt, that water does not politely refreeze in place. It flows into the oceans and gets redistributed across the globe. A lot of that meltwater ends up at lower latitudes closer to the equator. When that happens, you're literally taking mass that was nearer the rotation axis and moving it outward. That increases Earth's moment of inertia, the resistance to spin, even if the total mass of the planet stays the same. By conservation of angular momentum, if you increase the moment of inertia and there's no big external torque, the rotation rate has to drop. In simple terms, move mass outward, the spin slows down. The direct consequence is that on long timescales, continued polar ice melt should lengthen the day by tiny amounts, fractions of a millisecond spread over decades. So climate change, through ice loss and sea level rise, has a built-in effect on rotation, and it points towards slower spins and longer days, not shorter ones. That's the expected sign of the ice and oceans piece of the puzzle. But this is where the story gets more confusing, because the data since 2020 don't look like a simple climate is slowing the spin full stop picture at all. Here's the paradox. Climate change, through melting ice and mass moving toward the equator, should eventually make days longer. But the short days you've been hearing about since 2020 are the opposite. They represent a faster rotation, shorter days by around 1 to 1.5 milliseconds compared to the standard. That tells you something important right away. The climate signal from ice melt and long-term ocean warming is not yet the dominant player in the year-to-decade window you're living in. It's there, building in the background, but for now it is getting partially masked or even temporarily outweighed by other processes like atmosphere and core dynamics that can push the spin in the faster direction. So right now it's like having a slow, constant drag on a flywheel from climate change, while at the same time some other mechanism is occasionally hitting the gas. The net result is a rotation record that shows unusual short days, even though the physics of mass moving toward the equator says, in the long run, we should slow down. That's why scientists talk about superimposed signals. One is a slow trend from ice melt making days longer. Another is a more variable pattern from atmosphere and oceans, sometimes making days shorter. On top of that, there's the deep interior, the core doing its own thing that also affects rotation. The short days since 2020 are basically the visible tip of that complicated overlap. So the next question is, if the long-term climate signal is weaker now, does it ever take over? And if it does, what does that do to this whole negative leap-second problem? Some recent research points toward a future slowdown. As more polar ice melts and more water gets shifted from high latitudes down toward lower latitudes in the equator, the mass redistribution effect grows. Over decades, that should increasingly act to slow Earth's rotation. One prediction, often linked with work by researchers like Agnew and others, is that this growing climate-driven slowdown could eventually counteract the recent speed-up. In practical terms, as the climate keeps warming and ice keeps melting, the length of day could gradually start increasing again, pushing the system away from the conditions that would force a negative leap second. So you're in a strange window. Right now you have shorter days that are causing talk of deleting a second from the world's clocks. Over the longer run, the same human-driven climate change that's reshaping coastlines is expected to lengthen the day and reduce that pressure on UTC, shorter days now, longer days later, both tied to how water moves around the planet. That means the story is not climate change will make days shorter, or climate change will make days longer. The more accurate summary is, climate change is one player in a system where multiple big processes are fighting over milliseconds, and depending on the decade you look at, a different process can lead. And that naturally leads to the next layer down. If the air above you and the water around you can already push on the spin, what about the metal sphere deep under your feet, the inner core, that may be changing its own rotation relative to the surface? Right now, while you're watching this, there is a solid metal sphere deep under your feet that might be changing speed relative to the rest of the planet, and you will never feel it directly, but you will see its effects in the timing of your day. That sphere is Earth's inner core. Start with the basic layout. From the surface down to the centre is about 6,371 kilometres, roughly 3,960 miles. Somewhere around 2,900 kilometres down, about 1,800 miles, the solid mantle gives way to the liquid outer core, mostly molten iron and nickel. Inside that liquid shell sits the solid inner core, a metal ball about 1,220 kilometres in radius, around 760 miles. It's like a hot iron seed inside a sea of metal. For a long time, the standard picture was that the inner core rotates at almost the same speed as the mantle and crust, but not exactly. Seismic studies, where scientists look at how earthquake waves pass through Earth, suggested that the inner core might be rotating just a bit faster than the surface. That idea was called super-rotation of the inner core. More recent work, though, points to something more complicated and more interesting. Looking at decades of seismic data, some teams see signs that the inner core has been slowing down relative to the mantle and crust. In some analyses, it may even have crossed the line and started rotating slightly slower than the rest of Earth. So you have three layers that can move differently: the mantle and crust, which you stand on, the liquid outer core, and the solid inner core. The inner core is not locked to the surface like a rigid part of the same spinning sphere. It's embedded in liquid metal, and that liquid can let it lag or lead a little. The speed difference is tiny, maybe a fraction of a degree per year, but over years and decades it adds up. That raises the obvious follow-up question: if the inner core changes speed, how does that affect the spin you actually care about, the rotation of the surface? This is where core-mantle coupling and torque come in. The boundary between the liquid outer core and the solid mantle is not a clean slip surface like ice on ice. It's a complex zone where magnetic fields, viscous forces in the liquid metal, and even slight topography on the boundary all interact. Earth's magnetic field is generated by motion in the liquid outer core. Those moving conductive fluids interact with the mantle above through magnetic forces. You can think of the field lines threading through both regions. When the flow in the core changes, it can apply a torque, a twisting force, on the mantle. Viscous drag in the fluid and small irregularities at the core mantle boundary also allow some of the core's angular momentum to be transferred to the outer Earth or taken away from it. So if the inner core, through the outer core, changes its rotation rate, that change does not stay hidden at 5,000 kilometers depth. Over years to decades, angular momentum is shuffled between the deep interior and the solid shell you live on. The result is that the planet's surface rotation can speed up or slow down by milliseconds, not per day instantly, but as a trend that builds over long intervals. In other words, if the inner core decides to slow down a little relative to the mantle, that lost spin doesn't vanish. Angular momentum can flow outward, and the mantle and crust can speed up slightly to compensate. That shows up again as a shorter length of day in the records. The numbers are small, but the mechanism is powerful because it involves a huge mass of metal interacting with the rest of the planet. So the natural question is, are we actually seeing that in the real data? Or is this just a nice story? Some researchers do see correlations between changes in inner core behaviour and the anomalies in length of day and polar motion, especially since around the year 2000. Polar motion is the slow wandering of Earth's rotation axis relative to its crust, measured in meters at the surface. When scientists line up the timing of changes in inner core rotation inferred from seismic waves with the timing of changes in LOD and in how the pole wanders, they find patterns that look linked. It's not clean, it's not like flipping a switch and instantly seeing the day change by a fixed amount, but there are hints that when the inner core changes speed, or when flow patterns in the outer core reorganize, the Earth's rotation and its wobble respond over the following years. One hypothesis is that the post-2000 features in the LOD record, including the faster days after 2020, are partly driven by adjustments in the core, layered on top of all the atmospheric and oceanic effects you already heard about. This is why geophysicists talk about shared signals between core dynamics, LOD, and polar motion. The data seem to show that these things are not independent. When the core does something, the shell of rock and water and air reacts, but because everything is happening slowly and with multiple processes stacked on top of each other, it's hard to say exactly how much of the recent speedup is due to the core versus other contributors, so we're left with an uncomfortable position. We have a planet where the length of the day is clearly changing by milliseconds. We have evidence that the inner core is changing its relative rotation. We have correlations between core-sensitive signals and rotation anomalies, but we still do not have a simple, complete model that says, here is exactly how the core is driving this behaviour. And that's the unsettling part. You're watching planet-scale behaviour, shorter days, that likely involves a region you will never see directly. We cannot drill to the core, we cannot put instruments there. Everything we know about it comes from indirect tools. We use seismic waves from earthquakes that travel through the core and get recorded by seismometers at the surface. Tiny differences in how fast those waves arrive and how they bend tell us about the structure and motion deep inside. We measure small changes in Earth's gravity field from satellites, which reveal how mass is moving around. We track the exact wobble of the rotation axis and the exact length of day with radio telescopes and lasers. Then, from all of those pieces, we try to reverse engineer what the inner core and outer core are doing. It's like trying to understand the gears in a sealed engine just by listening to the sound and watching the wheels move. So when you hear that days are getting shorter by a millisecond, there is a good chance that part of that signal is literally the deep engine of the planet going slightly off its old script. Not in a catastrophic way, but in a way that shows the core, the mantle, the oceans, and the air are all tied together in one big, messy, rotating system. And if the deep core can quietly change its speed and push on the surface, that raises another question. What else about Earth's rotation is shifting that you don't feel directly, like the fact that the spin axis itself is wobbling around, making the whole planet walk in a kind of slow, drunken circle? You probably think of Earth's rotation axis as a fixed line through the North and South poles, but it isn't fixed at all. The axis actually wanders in a slow, small circle, and that motion shows up as a physical shift of the rotation pole by a few meters at the surface. This specific wobble is called the Chandler wobble, and it has a period of about 433 days, a bit longer than a year. At ground level, that means the point we call the North Pole can move by roughly 3 to 9 meters, around 10 to 30 feet around its average position. It's not drifting off toward Europe or Canada in some dramatic way, but it is not nailed to one exact point either. So what does that actually look like in practice? If you drew a dot where the pole should be and tracked where it really is day by day, you'd see it trace out a small loop around that mean position, taking roughly 14 months to complete one full circuit. That's the Chandler wobble. It's a natural mode of the way a slightly imperfect spinning Earth behaves, influenced by how mass is distributed inside and on the surface. This wobble is small compared to the size of the planet, but timing systems and precise geodesy can't ignore it. When you're aiming for centimetre or millimetre accuracy in positions and microsecond accuracy in time, a few meters of pole motion absolutely matters. The obvious question is, how is this wobble connected to the length of day problem we've been talking about? The key idea is that polar motion and day length come from the same basic source: changes in how mass is arranged inside the Earth system. When air pressure patterns shift, when ocean currents move large volumes of water, when groundwater is pumped and stored, when ice melts or accumulates, all of that changes where mass sits relative to the rotation axis. Those mass shifts don't just nudge the spin axis, they also alter the moment of inertia and therefore the rotation rate. So the Chandler wobble is not just some separate random dance of the pole, it's part of the same family of motions that also give you changes in length of day. Recent studies show that changes in the amplitude of the Chandler wobble how big that pole loop is at a given time, often line up with shifts in the length of day. When the wobble gets stronger or weaker, the timing of the day tends to show corresponding patterns after you filter out the obvious tidal and seasonal signals. In other words, the data are telling you that when the planet's spin axis moves differently, the length of the day is not far behind. That means any big shift in how this wobble behaves is a serious clue about what's going on under the surface and in the climate system. So did the Chandler wobble actually change in some unusual way that lines up with the current rotation anomalies? When scientists looked closely at satellite gravity data and detailed records of polar motion, they noticed something around the early 2000s. The average position about which the pole wobbles, and aspects of the wobble itself, shifted in a way that did not match the patterns seen in the previous decades. It was as if the baseline of Earth's drunken walk moved, and the shape of the walk changed too. This transition seems to connect to changes in the cryosphere, meaning the frozen parts of the Earth's system, and in the oceans. Large-scale ice loss from Greenland and parts of Antarctica, plus ongoing changes in ocean mass distribution, show up clearly in satellite gravity missions. Those same data sets, combined with polar motion records, suggest that the way mass is being rearranged on the planet has changed since around 2000. On top of that, you still have possible contributions from the core. If flow in the outer core and rotation of the inner core are changing, that affects how mass and angular momentum move at depth, and some part of that ends up expressed as both polar motion and changes in the length of day. So the early 2000s stand out as a kind of pivot point, where multiple subsystems, ice, oceans, possibly core, shifted enough to leave a mark in the wobble and the rotation. So now you're staring at a key question. Is the recent speed up in Earth's spin, the shorter days since 2020, actually tied to this altered wobble? Some scientists think the answer is at least partly yes. The idea is straightforward even if the math behind it is not. If you change how the planet leans while it spins by redistributing mass so that the pole's motion pattern changes, you also change the way angular momentum is shared inside the Earth system. That can in turn adjust the rotation rate at the surface. Under this hypothesis, the recent faster rotation is not just a separate event. It could be another expression of the same underlying shift that changed the Chandler wobble behavior around the early 2000s. Mass is moving, the pole's path changes, and the planet settles into a slightly different spin state, one that happens to give you shorter days for a while. The problem is that you're dealing with overlapping signals. Wobble effects, climate-driven mass changes, and core dynamics all operate on similar timescales and can produce similar signatures in the length of day record. It's hard to cleanly separate how much of the post-2000 anomalies, including the fast days after 2020, are due to wobble-related mass shifts at the surface, how much are due to deep core torque, and how much come from ordinary atmospheric and oceanic variability. So you end up with a situation like this. You know the axis is wobbling differently, you know the day length is changing in unusual ways, and you know ice and water and the core are all moving in ways that matter. You can match patterns and build models, but you still don't have a simple single cause you can point to. The planet's rotation is being pushed and pulled from above and below at the same time, and that leads straight to the next tension point. If slow, smooth wobble and deep interior flow can already tweak the length of your day, what about sudden violent events like giant earthquakes and massive volcanic eruptions, the kind of things that literally jerk the planet's mass in one instant? When people hear Earth's rotation changed, they jump straight to one idea: some huge disaster must have kicked the planet. So let's deal with that head on. Yes, giant earthquakes and eruptions really do change the length of the day, but not nearly enough to explain the millisecond scale speed up you're living through now. Start with earthquakes. A massive quake doesn't just shake buildings, it physically rearranges rock inside the planet. When that happens, the distribution of mass changes, and with it, Earth's moment of inertia, the how hard is it to spin this thing factor. If you shift dense rock a bit closer to the rotation axis, the moment of inertia goes down, and the planet can spin a tiny bit faster, just like bringing mass inward on a spinning object allows it to turn faster. but here at a very small scale. The 2004 Sumatra Andaman earthquake, with a magnitude over 9, is one of the biggest quakes recorded in modern times. Estimates from geophysical models suggest it shortened the length of day by around 2.7 microseconds. It also shifted Earth's figure axis, the axis tied to the mass distribution, by a few centimeters. To your senses, that change is zero. You don't feel a jolt in the length of the day. But to the instruments we use now, it's clear. With modern techniques, we can see that kind of microsecond scale change and centimeter scale axis shift. So yes, a single megaquake can make a measurable dent in the rotation, but here's the key: it's microseconds, not milliseconds. A microsecond is 1/millionth of a second, a millisecond is 1,000th of a second. The short days since 2020 are off by about 1 to 1.5 milliseconds. That's hundreds of times larger than the effect of that massive 2004 quake. So the obvious next question is, what if you stack several of these monsters together? Can a bunch of mega quakes add up to the millisecond changes we see after 2020? If you take the biggest earthquakes over the last few decades and add their estimated effects on the length of day, you do get a sum, but it still only reaches tens of microseconds in total, not full milliseconds. Even if your planet had an unusually busy century of large quakes, you'd still be short of the kind of sustained millisecond level speed-up we're measuring now. That's why seismologists say earthquakes show up as sharp spikes in the rotation data, little jumps at the times of the events, but not as a long-term trend of faster days. They leave fingerprints, not a new baseline. You can't explain the overall post-2020 pattern by pointing to tectonic disasters alone. So if earthquakes aren't driving the millisecond era, what about volcanoes? The other classic planet goes crazy image people have. Volcanic eruptions also move mass around. A major eruption can eject trillions of kilograms of ash and sulfur into the atmosphere and build new layers of rock on the surface. All that material has weight, and when you move weight upward and sideways, you tweak Earth's mass distribution. That can, in principle, change the rotation. But again, when you actually crunch the numbers, the effect on the length of day is mostly in the microsecond range. A big eruption might cause a tiny sharp change, but it is usually buried under the much larger atmospheric circulation changes that follow. The winds and pressure systems that develop after a major eruption, as the climate system responds to all the injected material, have a bigger cumulative effect on LOD than the direct "we moved some rock and ash" part. So the pattern is the same. Catastrophic events do matter, but they matter at the microsecond level, with effects that are sharp and localized in time. They are not giving you a consistent pattern of shorter days spread out over years. This leads to the main point you need to internalize. The recent spin-up of Earth, the millisecond short day since 2020, is not caused by anything cinematic. There is no single mega quake tearing continents apart, no super eruption flipping the planet's rotation like a switch. If that were happening, you wouldn't be watching a calm video about it. You'd be dealing with a very different world. Instead, what you're seeing is the quiet, cumulative outcome of fluid flows and deep dynamics. Air moving in jet streams, water shifting in oceans, ice melting and redistributing mass, liquid metal flowing in the core, the inner core adjusting its rotation, the pole wobbling differently. Each piece nudges the rotation by microseconds to fractions of a millisecond. Add those nudges over years and decades, and you get the sustained millisecond scale anomalies that force timekeepers to consider risky steps like a negative leap second. That's the uncomfortable contrast. The really big dramatic events, the ones you'd expect to change the day, mostly leave tiny, sharp blips. The smooth but strange changes you're actually dealing with, the ones that might break assumptions in global timing systems, come from subtle shifts you never see, layered over long intervals, ticking away into the background. So the danger here isn't a single catastrophic jolt to the planet's spin. It's the way small ongoing changes are quietly moving the rotation away from what your technology expects. And the next question is obvious. If the planet is already sliding away from the neat 24-hour model, what happens to the machines that assume a perfectly predictable Earth, especially the ones that live in orbit and turn timing into your exact position on the ground? The machines you trust to tell you where you are, down to a few meters, start from one basic assumption: they know exactly how fast Earth is spinning under them. The moment that assumption slips by even a millisecond, the math those machines use starts to drift. GPS is the cleanest example. GPS satellites orbit at around 20,200 kilometers above Earth, roughly 12,550 miles. Each one carries atomic clocks, not quite as perfect as the lab standards on the ground, but extremely stable. Those satellites constantly broadcast signals that include the time, according to their onboard clocks, and their own position in space. Your phone or your car or a receiver on a ship listens to several of those satellites at once. It measures how long it took each signal to reach it. Because radio signals move at the speed of light, the travel time tells you the distance. Combine distances to multiple satellites, and you can solve for your position in 3 dimensions and the exact time all at once. But there's a catch. Those distance calculations assume you know exactly where Earth is rotated to at that moment. The coordinate systems that turn distance to satellite A, B, C, D into you are here on this street are tied to an Earth that is spinning at a known angle. If the rotation angle is wrong, even by a tiny amount, the position you compute on the ground shifts. So GPS and similar systems like GLONASS, Galileo, Beidou all depend on very precise models of Earth's rotation. They use parameters that say, at this absolute time, Earth has rotated to this orientation, accounting for known wobbles, tides, and length of day variations. Those parameters are updated frequently, and the updates are based on the same Earth rotation data that show the millisecond scale weirdness we've been talking about. Now take that and connect it to a simple physical limit, the speed of light. Light travels about 300,000 kilometers in 1 second, about 186,000 miles. In 1 millisecond, 1,000th of a second, light travels about 300 kilometers, roughly 186 miles. Your GPS receiver isn't going to suddenly be off by 300 kilometers from a 1 millisecond error, because the geometry of multiple satellites and the way the algorithms work reduces the full effect. But the bottom line is still harsh. If you let Earth's rotation drift by just 1 millisecond in your model and don't correct for it, your inferred position can be off by hundreds of meters to kilometers, especially in sensitive or poorly constrained setups. For typical consumer use, the system is designed with margins and corrections, so you mostly see meter-level error. For critical systems like aircraft navigation, precision agriculture, and geophysical surveys, even tens of meters of error are unacceptable. So these systems have to update their Earth rotation models regularly, using the latest length of day and polar motion values. When the planet starts throwing unexpected millisecond changes into the mix, the pressure on those updates increases. The math can handle it, but only if the people running the time and reference frame services stay ahead of what the planet is doing. Now, fold leap seconds into this mess, and you see why time services get very nervous when someone says, "We might need a negative leap second." Every time we've added a positive leap second, we've done something simple in concept but awkward in practice. We stop the world clock for 1 second at the end of a day. There is a real moment when the timestamps go 23:59:59, then 23:59:60, then 000000. That extra label, 23:59:60, looks harmless on paper, but many systems were never written to handle it. In past leap second events, some servers froze because their code didn't know what to do with a time that wasn't in the usual 60 seconds per minute pattern. Some databases recorded the same time twice, causing confusion in logs and transactions. Some networks went out of sync because different parts of the system applied the leap second in slightly different ways or at slightly different moments. Engineers have worked around these problems over time, but they've mostly only had to deal with leap seconds that add time, never ones that remove time. A negative leap second is worse because it creates a minute with only 59 seconds. You go from 23:59:58 straight to 000000. The time 23:59:59 never exists. A lot of code and a lot of hardware simply assumes that seconds always increase by exactly 1 without skipping, and that every minute has either 60 seconds or, in some careful cases, 61 on a leap second. Very few systems have been designed, tested and certified with "we will delete a second" in mind. That's why organizations that depend on clean, continuous time are worried. They see a negative leap second not as a neat fix, but as a trigger for bugs that haven't even been discovered yet. So how do they try to avoid the shock of a 1-second jump, whether positive or negative? One of the main strategies already in use is called leap smearing. Instead of applying a 1-second correction at one instant, you spread that correction over a longer time window, like a few minutes or even an entire day. For example, if you need to add a second, you can slightly slow down the scale of your clock over several hours, so that by the end of that period, you've effectively gained 1 second without ever showing a weird 23:59:60 timestamp. Google, for instance, has used leap smearing on its internal time services. Other large tech companies, telecom operators, some data centers, and satellite control systems are experimenting with similar approaches. The idea is simple: avoid hard jumps in time that break assumptions, and instead make tiny, almost invisible adjustments to the rate of time that are easier for software and hardware to digest. Right now, these searing techniques are still somewhat specialized. Different organizations do them in different ways. There isn't a single global standard, which itself can create problems if two systems that talk to each other are smearing differently. But as Earth keeps delivering faster days, and as leap seconds become more painful to handle, these kinds of soft corrections start to look less like clever hacks and more like the new normal. If the planet keeps pushing us towards scenarios where we'd otherwise need a negative leap second, leap smearing and related techniques might be the only practical way to adjust. Instead of everyone bracing for a single risky second deletion, they quietly bend their timescales in slow motion and hope every system in the chain can keep up. So you end up in a strange position. Your phone calmly shows you your location and the correct time, but behind that calm surface there is a constant scramble to update rotation models, apply smears and avoid time jumps that could confuse global infrastructure. Milliseconds in Earth's spin are now directly connected to how safely planes fly, how accurately trades are time-stamped, and how well your navigation apps work. That brings up a different angle though. All of this is about machines, servers, networks and satellites. But what about you and every other living thing on Earth? If the planet's day changes by a millisecond or so, could any biological system actually notice? Or is this purely a human technology problem? Here's the key question. If Earth is quietly shaving 1 or 2 milliseconds off the day, can your body tell at all, or is this only a headache for satellites and servers? Your internal clock is not built from cesium atoms, it's built from hormones and neurons. Deep in your brain, in a region called the suprachiasmatic nucleus, groups of cells fire in daily rhythms. They respond to light, to a temperature, to your habits. Hormones like melatonin and cortisol rise and fall on roughly 24-hour cycles. This is an analog system, messy and adaptive, not a digital counter ticking perfect seconds. You already know from experience how sloppy but flexible this system is. You can fly across 6 or 9 time zones and your body will eventually adjust. That's a shift of several hours, tens of thousands of seconds. And yes, you feel jet lag while your internal clock and the local daylight fight each other, but you do adapt. Compared to that, a change of 1.5 milliseconds in the length of the day is microscopic. It's roughly 1 part in 60 million of the full day. That's like changing your height by less than the thickness of a human hair. Your neurons have noise, your hormone cycles have noise, your sleep patterns drift by minutes from one night to the next. A 1.5 millisecond change is completely buried in that biological fuzz. There is no mechanism in your body that can track the planet's spin at that resolution. You'll not feel it. Not now, not ever, not even if you focus and try. So if you can't sense millisecond changes, why even talk about biology here? Because Earth's day hasn't always been 24 hours, and life has gone through much bigger shifts in day length than anything happening today. Hundreds of millions of years ago, the day was shorter. In the late Devonian period, roughly 360 to 380 million years ago, evidence from fossil corals and layered tidal sediments suggests that days were around 22 hours long. Go back even further into parts of the Proterozoic eon, more than 500 million years ago, and the day length may have been closer to 21 hours. That means there were more days packed into 1 year. Instead of about 365 days, you're looking at roughly 370 to 400 day years, depending on the exact period. In very simple terms, your calendar would have had to fit in about an extra week's worth of sunrises and sunsets every year. The sun rose and set more often because Earth was spinning faster while still taking the same time to orbit the sun. Life did not collapse because of this. Organisms at the time adapted to whatever the current day length was. Evolution doesn't care about some abstract 24-hour ideal. It tunes internal clocks to whatever the environment provides. As tides, sunlight cycles and seasons interacted with a 21 to 22-hour day, biological rhythms locked onto that pattern. That history tells you something important. Biology can handle slow changes in day length over millions of years. As Earth's rotation gradually slows due to the moon's tidal drag, internal clocks in future species will just tune to the new reality. A day that is 24 hours and 2 milliseconds long, or 24 hours and 10 minutes long, is not a problem for evolution, as long as the change is slow, but that doesn't mean biology never cares about precise timing. Plenty of organisms do rely on very sharp cues. Some plankton rise and sink in the ocean following daily light changes. Birds time their migrations to seasons, which are keyed to day length. Plants open and close their leaves and flowers in response to the light-dark cycle. Many coastal species, like crabs and some fish, key off lunar cycles and tidal patterns. They don't know what UTC is, they respond to the actual sun and moon and the timing of light, dark and tides. As long as civil time, the official clock you use for work and school, stays roughly aligned with solar time, the behaviour of these organisms is unaffected by what humans decide. They follow the sky, not the network time protocol. Even if we mess up timekeeping for a bit with a bad leap second, the birds will still leave when the daylight pattern tells them to, not when your phone says 9 o'clock. But here's where it gets interesting. If humanity eventually decides to completely divorce official time from the sun to avoid leap seconds, and so will all the hassle, then our schedules can start to drift relative to actual daylight. Biology doesn't change, but our social structures do. Picture this in simple terms. Right now, noon is roughly when the sun is highest in the sky for your location, maybe offset by time zones, but still roughly aligned. If we let UTC slowly slide away from Earth's rotation without ever correcting in a few centuries or more, the sun at 12 o'clock might not be close to the top of the sky anymore. It could be noticeably to the west or east, depending on how the drift is managed. Your body, which still responds strongly to real light, might start to feel a mismatch between the socially defined middle of the day and the actual brightest part of the day. That leads straight into the more psychological part of this story. Technology can handle drift if we plan for it. Biology can adapt over long times. But your sense of what a day is sits in between. It's a mix of physiology and culture. So think a bit further ahead, not 5 years, but hundreds. Suppose we go ahead with the plan to phase out leap seconds and then let civil time slide very slowly away from UT1. The current rules are set up to keep that drift manageable, and there are ideas to insert much rarer, larger corrections later. So you are not going to wake up in a world where noon suddenly means midnight. That's not on the table, but even a drift of a few minutes over a long stretch can feel wrong. We are used to the clock reinforcing what the sky shows. Lunch is when the sun is high, evening is when it gets dark, midnight is when it's long past sunset. If you push the system to the extreme in thought experiments, centuries without any correction, you reach a scenario where 12 o'clock on your clock could correspond to what your brain and eyes would currently file as mid-afternoon. That's not going to happen soon, but just the fact that it's possible tells you how artificial our time labels really are. A small change today, like a millisecond off the day length, seems meaningless, yet the consequences accumulate not in your biology directly, but in how we define, track, and schedule life around the planet. The strange part is this: physics is telling you that days are not perfectly stable. Biology is mostly fine with that, but civilization has built a rigid framework of numbers on top of something that is slightly flexible. The tension you feel in this story comes from that mismatch. The planet is drifting by milliseconds. Your body doesn't care, but your systems and your sense of order do. And that sets up the next question. If we zoom out from you and your sleep cycle to the entire history and future of Earth, how do these tiny, present-day anomalies fit into the much bigger picture of a planet whose day has been changing for billions of years and will keep changing long after our current time standards are obsolete? Right now, you're stressing about milliseconds, but on the timescale of Earth's history, the whole 24-hour day you're used to is just a temporary setting. The planet has not always spun this way, and it won't keep this exact rhythm forever. Take the dinosaur era as a reference point. In the late Cretaceous, around 70 million years ago, a day on Earth was roughly 30 minutes shorter than it is today. Instead of about 24 hours, you're looking at around 23.5 hours. That's not a guess pulled out of nowhere. It comes from two things that agree with each other: tidal physics and fossil records. Tidal physics says that the moon's gravity pulls on Earth's oceans, raising tides. Those tides rub against the seafloor and coastlines, turning rotational energy into heat. That slowly drains angular momentum from Earth's spin and transfers some of it to the moon's orbit, pushing the moon gradually outward. Over tens or hundreds of millions of years, that process must make days longer and months longer. Fossil corals and certain sediment layers called tidal rhythmites give you a direct timestamp from the past. Some ancient corals laid down daily growth bands and seasonal bands. When scientists count how many daily bands fit into 1 year's cycle in those fossils, they find more than 365 in the late Cretaceous, around 372 days per year. That matches a shorter day length by roughly half an hour. Same year length in terms of orbit around the sun, more spins per orbit. So in dinosaur time, the planet squeezed in about a week's extra sunrises into each year. Nobody back then felt some sudden shift from 365 days to 372 days. The change happens slowly over millions of years. But from your perspective, looking back with numbers, the difference is big. Move further back and the effect grows. Earlier in Earth's history, the day was even shorter. The general pattern is clear. Early Earth spun faster as time passes, tidal friction slows the rotation, days get longer, the moon moves farther away. So if we know tidal friction is doing this, why doesn't the day just lengthen at a perfectly smooth rate? Because the strength of tidal friction is not fixed. It depends on how the oceans are shaped and how they resonate with the tides. When all the continents are clumped together in a supercontinent, you have different ocean basins, coastlines, and seafloor structures than when the continents are scattered all over the globe. Those shapes control how tides slosh around and where energy is dissipated. On 100 million year timescales, when supercontinents form and break apart, the pattern of tidal dissipation changes. Some configurations of continents and seafloor topography drain rotational energy faster, some slower. That means the rate at which Earth's spin slows isn't just set by the moon's pull, it's modulated by plate tectonics and ocean geometry. So for example, during some geological periods, Earth might lose rotation energy faster, and the day lengthens more quickly per million years. During others, the same tidal process is less efficient and the day lengthens more slowly. That's why scientists talk about a long-term trend of slowing spin, but with a rate that varies depending on where you are in the supercontinent cycle. Now, stretch your view out even further, not million, but billions of years into the future. If you just let tidal friction run and you ignore everything else, there's a natural endpoint. Over a very long time, Earth's rotation would tend to synchronize with the moon's orbit. That's called tidal locking. In that scenario, one side of Earth would always face the moon, the same way one side of the moon always faces Earth now. A day relative to the moon would match the moon's orbital period. The planet would spin once per lunar month. That would mean a much longer day than 24 hours measured in our current units. Will this exact state ever be reached? Realistically, probably not, because the sun is evolving too. In a few billion years, the sun will brighten and then expand as it moves off the main sequence. Long before perfect Earth-Moon tidal locking is achieved, changes in the sun will be dominating everything. Oceans may boil away, the whole system changes. But the important point is that the endpoint physics is the same physics nudging your day length right now. The same tidal friction that is stealing microseconds from the spin over centuries is, over billions of years, trying to push the Earth-Moon system into a synchronized configuration. What seems like a tiny effect in your lifetime is the visible edge of a very slow, very large process. Now pull all of this together with what's happening today. On the scale of Earth's full history, the current millisecond level speedup is a tiny noise signal sitting on top of a big smooth curve. That big curve is the long-term trend toward longer days. Tides shaped by continents and seafloor are steadily draining rotational energy and lengthening the day, on average, over millions of years. Zoom out far enough, and the recent kink in the rotation record around 20 to 20 barely shows up. It's a small wiggle in a line that overall slopes towards slower spin. In another 100 million years, nobody plotting day length versus time is going to panic about a 1 to 2 millisecond dip that lasted a few decades. But zoom all the way in, down to the level of satellites, stock exchanges, power grids, and navigation systems, and that same tiny noise is powerful enough to force global timekeeping standards to change. It's enough to trigger debates about negative leap seconds, to push international bodies to vote on phasing out leap seconds, and to make engineers quietly rewrite core software that assume days are always 86,400 seconds long. So you're in a strange position in history. Cosmically, this is a small wiggle. Technologically, this is a big problem. The physics that slowly turned dinosaur days from 23.5 hours into your 24 is still running. But for a brief window, the local fluctuations from atmosphere, oceans, ice, and core are big enough to matter more than the smooth tidal trend. Your era is basically a zoomed-in frame on a long movie. In the wide shot, Earth is on a smooth, predictable path toward longer days. In your close-up, the frame shakes just enough that you have to rethink how you define time, coordinate a planet, and design machines that assume the ground beneath them spins with clock-like regularity. And that leaves another question hanging. If the long-term physics is already so far beyond anything we can control, could we ever, even in principle, push back and deliberately change Earth's spin ourselves? Or are we permanently just passengers on this rotating rock? You keep hearing that Earth's spin is changing under the influence of air, water, ice, and the core. So the obvious next thought is, could we ever push back on that and deliberately change how fast the planet rotates? On purpose? If the length of day really matters for our systems, couldn't a future civilization just fire some engines, or move some mass, and dial the spin to whatever it wants? The short answer is no, not in any controlled practical way. The numbers are brutal. Start with the thing that sets the difficulty, Earth's moment of inertia. That's the measure of how hard it is to change the spin of something. And for Earth, it's roughly 8 times 10 to the 37 kilogram square meters. You don't need the exact details, just note the size, a 1 with 37 zeros worth of resistance to spin change. If you wanted to change the rotation speed by even 1 part in a billion, that's like changing a 24-hour day by a few hundredths of a second. You'd need an angular momentum change on the order of 10 to the 28 kilogram square meters per second. That is the amount of spin momentum you'd have to add or subtract. Now compare that to what rockets can do. Even our biggest launch vehicles push maybe thousands of tons of propellant out the back at a few kilometers per second. The total angular momentum they give to Earth, as a whole, is tiny. Even if you pointed every rocket we've ever built the same way, and fired them specifically to try to twist the planet, you'd still be many, many orders of magnitude short of that 10 to the 28 requirement. You could launch rocket after rocket for centuries, and all you do is add noise buried inside the natural millisecond level fluctuations the planet already has. In other words, rocket engines are good at moving spacecraft, not planets. They can throw tens or hundreds of tons into orbit, but they barely scratch the angular momentum budget of something that weighs nearly 6 times 10 to the 24 kilograms and has that huge moment of inertia. So then the thought experiment moves to a different kind of lever. If you can't push the spin directly very much, what if you cheat by moving mass around on the surface? In principle, if you take mass from near the equator and move it toward the poles, you reduce Earth's moment of inertia and speed up the rotation slightly, just like a spinning skater pulls in their arms and turns faster. Do the reverse, move mass from high latitudes out toward the equator, and you increase the moment of inertia and slow the spin down. The physics is clean, but the scale is extreme. You would need to move trillions of tons of material to get meaningful permanent changes in day length. We're not talking about a few dams or cities here. We're talking about something on the scale of entire mountain ranges. Think about the Himalayas, thousands of kilometers long, multiple kilometers high, with a total mass in the range of many trillions of tons. To noticeably speed up Earth's spin by a fraction of a millisecond, you'd be looking at a project on the order of relocating a Himalaya-class mass, starting near the equator and stacking it closer to the poles. That's not big construction. That's planetary engineering beyond anything remotely plausible with human technology, even if you imagine far future megastructures. And remember, it's not enough to move that mass temporarily. If your goal is a sable change in day length, the mass has to stay where you move it, for geologic timescales, without sliding back due to erosion, tectonics, or simple gravity-driven flow. You're fighting not just engineering limits, but the planet's own tendency to relax into lower energy shapes. So then you might think, what about something far more violent, like artificially slamming big objects into Earth to spin it up or down? Take a kinetic bombardment scenario. Suppose you drop a metal asteroid about 10 kilometers across, moving at tens of kilometers per second. That's in the range of civilization-ending impacts. The amount of kinetic energy is enormous. And yes, that impact would technically change Earth's angular momentum. But most of that energy and momentum doesn't go into a clean change in global spin. It goes into heat, shockwaves, vaporizing rock, throwing material into ballistic trajectories and slightly altering Earth's orbit and the impactor's path. The part that becomes a permanent, coherent change in the planet's rotation rate is a small fraction. You might manage microsecond scale changes in length of day, but the lasting millisecond plus changes you're thinking about are still out of reach as a clean, controllable outcome. And of course, if you're dropping 10-kilometer asteroids on purpose, you've already lost in every other sense. The crust would be devastated, climate would be wrecked, ecosystems would collapse, you'd change the spin a bit and destroy the conditions that make precise timekeeping meaningful in the first place. So rockets are far too weak. Moving mass is unimaginably hard at the required scale, and kinetic impacts are destructive and still not efficient at delivering neat, long-lasting spin changes. That leaves you with one clear conclusion. When it comes to Earth's rotation, nature is already operating near the maximum range you can get without tearing the planet apart. The millisecond level oscillations in length of day that we're observing now are pretty much the upper limit of what can happen from ordinary, natural processes, meaning air, water, ice, and liquid metal shifting around, plus modest tectonic movements. To get changes much larger than that, you'd need truly catastrophic planet-reshaping events, things like the giant impacts that formed the moon, or completely reorganize the mantle early in Earth's history. Those kinds of events are not subtle, and they are not survivable for civilizations like ours. So in practice, the band of variation you're seeing now, milliseconds up and down over years to decades, is the full playground you will ever experience as a technological species. Earth won't suddenly drop to a 23-hour day without global destruction, and you won't slow it to 25 hours with any engineering project you can realistically build. That means you're stuck in a very specific role. You do not control the spin, you only react to it. Nature sets the pattern through fluid flows and solitidal drag, and you scramble to keep your time system, satellites and infrastructure synced to whatever the planet decides to do. So the real issue is not can we change Earth's spin, it's how dangerous are these natural changes for us if we can't really do anything to stop them. Is there a real threat in a couple of milliseconds shaved off the day, or is the danger hiding somewhere else, in the brittle assumptions we've baked into our technology? The first thing you need to hear very clearly is this: your day is not about to drop to 23 hours or jump to 25. The changes we're talking about are at the millisecond level, not at the hour level. There is no known physical mechanism that can suddenly remove an hour from the day without wrecking the crust, the mantle, and everything living on top. To take that much angular momentum out of the spin, or add that much, you'd need an event in the same league as the impact that formed the moon, or a complete rearrangement of the planet's interior. If that happened, we wouldn't be talking about GPS glitches, we'd be talking about survival. Right now, the rotation changes are subtle and slow. They are driven by fluid flows in the atmosphere and oceans, by mass moving as ice melts or accumulates, and by deep interior dynamics in the core. These processes move huge amounts of mass, but they do it in a way that only nudges the length of day by milliseconds up or down. The planet is not losing control of its spin, it's just not perfectly smooth. So physically this is small. No sudden 23-hour day, no instant climate collapse from rotation alone. If the physics is that tame, why are the people who run time services and global networks so tense about it? Because your infrastructure is brittle in very specific ways. Almost every digital system you rely on is built on simple timing rules. Rules that came from a world where it was convenient to pretend that days are perfectly regular. The assumptions look innocent. Things like every minute has 60 seconds and every day has 86,400 seconds, or on rare leap second days, 86,401, but never less than 86,400. As long as Earth's rotation only drifts slowly in one direction, and we only ever need to add the occasional positive leap second, those assumptions mostly hold. You add a second at the end of the day, the count goes up, and then you go back to business as usual. But a negative leap second breaks that pattern. Suddenly you're saying, today has 86,399 seconds, and your minute goes 23, 59, 58 straight to 0, 0, 0, 0, 0, 0, skipping 23, 59, 59 completely. Lots of code was never written with that case in mind. Operating systems, databases, logging systems, stock exchange matching engines, satellite control software, many of them have buried assumptions about how time steps forward. If you violate those assumptions, you can get crashes, duplicated or missing records, systems that disagree on the order of events, or devices that simply lock up because a timestamp shows a value they were never prepared to see. And so the real concern for engineers is not will tides rip the planet apart, it's will some untested corner of our software stack melt down when we try to delete a second from the clock? They worry about software bugs and synchronization failures, not about the physics of the spin itself. The planet can handle a 1 millisecond change easily. A trading platform or navigation system, running code written years ago by people who assumed time would behave nicely, might not. That leads to the deeper point. The main risk here is in the mismatch, not in the raw physics. Earth doing strange but physically reasonable things is fine. It's just a rotating body obeying conservation of angular momentum. The danger shows up when planetary behavior and human conventions drift away from each other. We built time zones, trading windows, air traffic schedules, satellite protocols and power grid control systems around the idea that 24 hours is a fixed fundamental thing. We treat midnight, 6 o'clock, 12 o'clock, 18 o'clock as anchors that mean the same thing everywhere, every day. Under the hood, we map that onto a rotating Earth, but we quietly assume the spin would change slowly and in one direction toward longer days. Now we're discovering that at the millisecond level, Earth does not respect that neat story. It speeds up, it slows down, it has anomalies tied to the atmosphere, the oceans, the cryosphere, and the core. The 24-hour day turns out to be a moving target we've frozen into a number. Our protocols assume a clean grid. The planet is giving us a slightly wavy line. When those two things don't match, you get stress at the join. That's when you start enforcing leap seconds, when you start inventing leap smearing, when different countries and organizations have to negotiate about how to keep time in a way that won't break global systems every few years. The weird part is not that Earth is misbehaving, it's that we built a civilization on top of a simplification that was always a little wrong. So where does that leave you right now in the early 21st century, watching milliseconds of rotation-drive debates in international committees? You're living through what will probably look in hindsight like a calibration event. For decades, the working assumption was simple: Earth is slowing down overall. We'll always need positive leap seconds once in a while, and that's annoying but manageable. Then after around 2000, rotation data started to bend away from that picture. By 2020 and beyond, you were seeing some of the shortest, fastest days in the precision record, strong enough to raise the serious possibility of a negative leap second, that forced timekeepers to confront a choice. Do we keep patching UTC with increasingly awkward leap seconds, including risky negative ones, or do we admit that tying our main timescale so tightly to Earth's rotation is no longer practical for a planet covered in software? The 2022 decision to phase out leap seconds by around 2035 is a direct answer to that. It's not just a policy tweak, it's a recognition that Earth's spin's too messy for the old rules. Future textbooks may look back on the post-2020 period as the moment when we realized we had to redefine timekeeping, not because of some giant disaster, but because Earth quietly refused to follow the smooth, slowing-only trend we expected. They'll show a plot of length of day anomalies, point to the kink, and say this is when we had to change the rules. In other words, the danger and the importance are not in hour-level changes to your day. They're in this subtle, annoying discovery that our super-precise clocks have outgrown the planet's ability to behave like a perfect metronome. We're recalibrating how we mesh human time with planetary time, under pressure from a few stubborn milliseconds. And that raises one last, sharp question. If tiny deviations in spin are enough to force a redesign of world time, how are we actually measuring these deviations with such confidence in the first place? And how sure are we that something really did change around 2020, instead of this all being a measurement illusion? You keep hearing that Earth's spin has definitely changed, that days really did get shorter around 2020, so it's fair to ask, how do scientists know that with enough confidence to rewrite global time rules? This isn't guesswork from a couple of clocks in a basement. There is a full measurement system wrapped around the planet, watching it spin in real time. One of the main tools is called Very Long Baseline Interferometry, VLBI. Here's the basic idea. You take radio telescopes separated by thousands of kilometers on Earth, and you point them at distant quasars. Quasars are incredibly bright, incredibly far away radio sources, basically fixed reference points on the sky for our purposes. The same wavefront of radio emission from a quasar hits different telescopes at slightly different times, because Earth is rotating and because the telescopes are spread out over the surface. Those tiny differences in arrival time down to trillionths of a second are recorded very precisely. When you compare them, you can solve for exactly how Earth is oriented in space at that moment and how that orientation is changing over time. If the planet spins a little faster or slower, those timing differences change in a way you can measure. From long VLBI time series, you can extract length of day variations as small as a few millionths of a second. So when you hear that a specific day was 1.59 milliseconds shorter than the standard, that's not guesswork from a wristwatch. That's a conclusion backed by global interferometry, atomic timing, and a lot of math. But VLBI is only one part of the picture. Scientists also use satellite laser ranging and dedicated gravity missions to track how mass moves around on and inside Earth, and then tie that to changes in rotation and wobble. In satellite laser ranging, ground stations fire short laser pulses at satellites equipped with special reflectors, basically very precise mirrors. The pulses bounce back and stations measure the round-trip travel time of the light. Because light speed is known, that gives distances to the satellites with millimeter-level precision. Repeating that over time lets you track the satellite's orbits very accurately. When you combine those distance measurements from many stations and many satellites, you get a detailed picture of how Earth's gravity field and shape are changing. Missions like GRACE and its successor take this further. They fly twin satellites in formation and measure tiny changes in the distance between them as they pass over regions of slightly stronger or weaker gravity. Those gravity variations are caused by mass movements, water shifting in aquifers and ice sheets, ocean currents, seasonal snow, and so on. When those gravity and mass movement data are compared with rotation and polar motion data, you can directly link "here's where the water and ice moved" to "here's how the spin and wobble changed." That's how we know, for example, that parts of the early 2000s shift in polar motion and rotation lined up with changes in the cryosphere and oceans. All of that feeds into the services that actually decide what time it is for the planet. Organisations like the International Earth Rotation and Reference System Service, IERS, collect data from VLBI, laser ranging, GNSS, like GPS, and other techniques every day. They maintain the official Earth orientation parameters, which include UT1 to UTC differences, polar motion, and length of day variations. IERS publishes regular bulletins. Bulletin A for rapid short-term predictions, and Bulletin C for official leap second announcements. When a leap second is needed, it's because those bulletins show UT1 drifting too far from UTC. That's the pipeline. Raw measurements of Earth's orientation and spin, processed into rotation parameters, fed into time services, and then into decisions like add a leap second on this date. If we ever face a negative leap second, it will come from exactly this chain. Now comes the crucial part. Do those measurements really say that something changed around 2020? Or is this just people overinterpreting noisy data? To answer that, scientists take the length of day record and systematically subtract out everything we already understand. They remove the regular tidal effects from the moon and sun. They remove the strong annual cycle from the atmosphere. They correct for known El Niño and La Niña events, for well-characterized ocean patterns, for long-term tidal trends. What's left after all that is the residual, what you can't easily explain with the usual suspects. When they do that, they see a clear feature. Around the late 2000s into the 2020, the residuals show a trend change. After decades where the average length of day was slightly longer than 86,400 seconds, the curve bends, and we start getting a cluster of days that are shorter than the standard, by around 1 millisecond or more. The short days of 2020 and the renewed short days in 2025 stand out against the previous half-century of precision records. Even after you account for tides, seasonal winds, El Niño and La Niña, and standard atmosphere-ocean models, there is still an extra signal. That extra signal is what points toward an additional driver influencing Earth's spin, something in the core, in the way the pole is wobbling, or in a combination of deep and surface processes that we haven't fully decomposed yet. That's why you hear phrases like unprecedented in the last 50 years from the people working on this. It doesn't mean nothing ever happened before 1970. It means in the era of modern high-precision VLBI, satellite ranging and atomic timekeeping, we have not seen this exact pattern of sustained short days and residual trends until now. So to sum up this part of the story, tiny changes in Earth's spin are not rumours, they're measured through. Radio telescopes timing distant quasars to track Earth's orientation with insane precision. Lasers and gravity satellites watching mass move around the globe in millimetre detail. And global time services like IERS continuously comparing Earth's actual rotation against atomic time. All of those streams agree on one thing. Something in the way this planet spins changed character around 2020, and we cannot fully explain it with the standard atmosphere-ocean tide picture alone, and that sets you up for the final turn in this whole narrative. If we're already seeing Earth act off-model at the millisecond level, and we're about to rewrite global time to cope with it, what happens if this is just the start of a longer, more complex swing in the planet's behaviour? Right now, your planet is not behaving the way the simple model said it should. The long-term picture says days should slowly get longer as the moon's tides drain rotation energy. Short-term, we expected mostly random wiggles around that slow trend. Instead, in just a few decades, the data gave you a sharp bend in the curve, a real before and after. For most of the late 1900s and early 2000s, the average day was a tiny bit longer than 86,400 seconds. That matched the basic story. Earth is gradually slowing down. Then around the 2000s, the curve started to flatten. By 2020, it didn't just flatten, it turned. You got a run of unusually short days, some about 1.5 milliseconds too fast, and then hints that things might swing back again. So instead of a smooth glide toward longer days, you're staring at a rotation record with a kink. Slightly longer days, then suddenly shorter ones, then a possible reverse coming. That's not the neat single arrow trend that old textbook diagrams like to show. The physics of tides didn't vanish, but something else climbed onto the stage and started pushing in the opposite direction, hard enough to show up against the tidal background. So the natural question is, what is actually driving this off-model behaviour? Right now, scientists keep coming back to three main suspects, and the hard part is that they're all acting at once. The first is core dynamics, changes in the flow of liquid metal in the outer core and in the relative rotation of the inner core. Those flows generate Earth's magnetic field, and they can also transfer angular momentum between the deep interior and the mantle. A small slowdown or speed up of the inner core relative to the mantle, spread out over years, can show up as length of day changes of milliseconds. The second suspect is mass redistribution from ice melt and oceans. As Greenland and Antarctic ice lose mass, and as ocean heat content and circulation patterns change, water moves around the globe. Some of it shifts toward lower latitudes, changing the moment of inertia and tending in the long run to slow the rotation. On shorter timescales, ocean current changes can either add to or subtract from the speed, depending on exactly where the water goes. The third suspect is polar motion and the Chandler wobble. When mass moves in the atmosphere, oceans and cryosphere, it doesn't just tweak the spin rate, it also changes how the rotation axis sits relative to the crust. That wobble feeds back into the angular momentum budget of the whole system. Changes in the amplitude and phase of the wobble appear to line up with parts of the post-2000 rotation anomalies. The problem is you're not watching one clean experiment where you can isolate a single variable. You're watching three overlapping ones on a live planet with no reset button. Core flows evolve, ice melts, oceans adjust, the wobble shifts, and the atmosphere reacts on top of all of that. Each process can produce signals in length of day and polar motion that look similar in size and timescale. When you try to separate them, you're doing forensics on a system where all the fingerprints are smeared together. So while the community can say climate is doing this, the core is probably doing that, and the wobble looks different after 2000, nobody can yet point to a single master knob and say, this is the exact reason your days were shortest in 2020 and again in 2025. That uncertainty is exactly what makes this feel like the beginning of something, not a closed case. Now connect that messy physics to something very concrete in your near future, the way official time itself is about to change. By around 2035, international timekeepers plan to change how UTC works. The current plan is to stop inserting regular leap seconds, or at least to suspend them for decades, and instead let UTC drift more freely away from UT1, the rotation-based time. That means the main timescale used by phones, computers, and networks will no longer be forced to track Earth's spin within a strict plus or minus 0.9 second window. Why are they doing this? Because the rotation behavior you're seeing now makes the old system too fragile. Positive leap seconds were already painful. The possibility of a negative leap second triggered by days in 2020 to 2025 that were about a millisecond and a half too short turned that pain into real risk. Many systems are simply not ready to delete a second. Rather than walk into that minefield every few years, timekeepers have decided to redesign the whole approach. That means you are living through a period where real measurements of Earth's spin, down at the millisecond level, are directly driving policy decisions about how humanity defines and distributes time. The data plots from these years are not just going into research papers, they're going into rule changes for the entire global timing infrastructure. So here's where you end up when you zoom out from all of this. You live on a world where continents drift over tens of millions of years, rearranging ocean basins and tides. Magnetic poles flip and wander as the core's flow reorganizes. Ice sheets grow and collapse, moving enough mass to tug on the rotation axis. And now, on top of that, days themselves are quietly changing length at the millisecond level, fast enough in timing terms to break the assumptions built into your technology. A handful of milliseconds per day sounds trivial, but it's enough to force humanity to rewrite its definition of time, to change UTC, to rethink how closely our clock should follow the rotation of the planet. And the uncomfortable truth is, we still don't fully know why this is happening right now in this exact pattern. We have good suspects, strong hints, and models that explain parts of the picture, but not a single clean answer. That's the real unsettling part. The issue is not just that Earth is spinning a little faster for a while. It's that a civilization built on precise atomic time is discovering that the world it's sitting on is a little less predictable than the clocks it invented, and that our systems have to bend to the planet, not the other way around. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.